So today my name is BT23CME031 and today we'll be seeing a problem on heat transfer with internal energy source, that is electrical heating of pipe. So the system is like this: energy generated in a cylindrical pipe wall of length L. Its inner radius is kappa R, outer radius is capital R. Electrical current is provided and there is a heat source SE with the pipe wall. The inner surface is insulated and heat dissipated to the surrounding at T by Newton's law of cooling. Now our first aim is to solve this problem and to derive the equation of the profile equation of temperature with the help of shear balance, and secondly we'll develop a profile equation with the help of um, equation of change, and we'll solve some numerical as well. So let us solve this question by shear balance approach. So we'll assume some assumptions, that is steady state, that is del T by dt equal to 0 at temperature at any point, and one dimensional flow. Heat flows in radial r direction and axial z and angular theta heat losses are neglected due to insulation or capping. Okay. So, and third assumption is uniform heat generation. Electrical heat source SE is constant throughout the pipe material. Then coming to the shell balance, heat in is given by QR at R, heat out at R plus delta R, QR plus delta R equal to this area into flux. Then heat generated equal to volume into heat generated per unit volume. Then putting this all together and dividing the equation by 2 pi R L, that is volume of shell, we get this equation. Then taking limit delta R tends to 0, transfer the first term into derivative, we get this equation for SE. Then applying boundary condition at R equal to kappa R inner surface QR, that is flux equal to 0, at small r equal to capital R outer surface, there must be flux which is convective flux and given by Newton's law of cooling. Then our task is to find governing equation for temperature. Then what we'll do is integrate differential equation in question form. Integrating with respect to r, we get this and a constant C1. Then we'll find the constant C1 by applying boundary condition, and we got this equation of flux and constant this. Then integrating for temperature T and substituting Fourier's law of conduction into the flux expression, we got this equation. Then rearranging for temperature gradient, we got this equation, and integrating second time with respect to R, we'll get this equation, where constant C2 is additional. So we need to determine constant C2 by applying second boundary condition, that is at T equal to T1, R equal to capital R, and we got C2 as this. Then substituting C2 in this equation, we got profile equation for T. Now this was for shell balance approach. Now we'll solve the same question by equation of change. So the governing equation change for this cylindrical by using cylindrical coordinate is expressed as this equation, and applying physical constraints such as steady state and no fluid motion means velocity at r, theta and z direction equal to 0. One dimensional radial conduction, del t by del theta equal to 0 and del t by del z equal to 0. And equation simplifies to second order differential equation as this. Then integrating this equation, we got temperature gradient. That's this. Integrating both sides with respect to r, we got this dt by dr and a constant C1. Dividing by r, we got differential equation of temperature with respect to r. Now we apply boundary condition 1, that is surface r equal to capital R is insulated and temperature gradient del T by dt dr equal to 0. So solving for C1, we got value of C1, and putting C1 into expression of dt by dr, we got this equation, and integrating this, we got capital T equation. Now we further need to calculate C2, applying second boundary condition at R equal to capital R, surface is maintained at temperature T1. So calculating C2 and putting into equation, we got profile equation for T by equation of change. Now we need to calculate some numericals, and problem statement is this: we need to find radial position R, calculate maximum allowable volumetric heat generation SC, and determine temperature at outer surface T1. So this data is given to us. Now what we need to do is uh, at the inner boundary at small r equal to kappa r is insulated, meaning heat flux and temperature gradient are zero at that point. Because heat can only escape through the outer surface, the temperature must increase as we move from cooling surface toward the insulated surface. So the heat insulated boundary where small r equal to r, maximum temperature will be there. That is at small r equal to 0.07. Clear? Then we need to calculate maximum allowable volumetric heat generation SE. To find small SE, we need to calculate temperature drop, and temperature drop will be given as this equation. Using formula derived in question 2 and question 3, we can arrive to this equation. Now putting into all values, we got LHS equal to 80 minus 20, this, then conduction term, that is this one, equal to this, and convective term external, we got this. Solving for SE, putting all values into equation, we have only SE unknown, so we can get SE. So the next question is to determine temperature at outer surface. We have the right to this equation of temperature profile, and we have everything given in the question in the form of values. So we will put everything in the equation and get T1. And next question is our question number 4. In that we need to calculate temperature difference T1 minus TA, calculate total electrical power required to maintain steady state, and quantitatively explain how power required P would change in an inner wall insulated field. So our step, this data is given to us. We need to calculate temperature difference. To find temperature difference between outer and inner air, we first need volumetric heat generation SE. We use total temperature drop equation, wall to embed. So did this temperature drop equation, then plugging into all values into this equation, we got this equation. Only SE is unknown, so we can calculate SE, and SE's unit will be watt per meter cube. Now using Newton's law of cooling for outer surface, we can calculate T1 minus TA. Then we need to calculate electrical power in kilowatt. So first we must know our volume. So volume is pi r square 1 minus k square into L. We got V. Then power calculation, power is equal to SE into V. So we have SE and we calculated V above it, so we can get power. Then quantitative effect of insulation failure. If insulation is failing, then heat leakage will occur. Maintaining to keep inner surface at require 500 degrees Celsius while heat is being lost, the interior leak, the rate of heat generation SE must be increased. Conclusion: to electrical power requirement P would increase significantly to compensate for additional heat losses and maintain the steady rate processing temperature. That's it. That was the all 4 question all about. Thank you.